In this video, we will see examples of computing probabilities involving two mutually exclusive events. First of all, I would like to remind you that two events are mutually exclusive if it is impossible for both of them to occur at the same time. In other words, the intersection of two events that are mutually exclusive is always going to be equal to 0. Events A and B are mutually exclusive. Suppose event A occurs with probability of 1700th and event B occurs with probability of 3100th. Compute the probability that B occurs or A does not occur or both. First of all, I would like to summarize what we know. Probability of A is 1700th, probability of B is 3100th, and A and B are mutually exclusive. First statement asks us to compute the probability that B occurs or A doesn't occur or both happen. In a more symbolic format, we write probability of B happening or A not happening. Well, if they are mutually exclusive, we can guarantee that if B happens, A automatically doesn't happen. So this probability is in reality the probability of A not happening. And we can use the complement rule and say a complement of A is same as 1 minus probability of A. We are given the probability of A to be 1700th, therefore 1 minus 1700th happens to be 8300th. Second part B, is asking us to compute the probability that either B occurs without A occurring, or A and B both occur. In symbolic form, it means probability of B occurring at the same time as A does not occur. So B occurs without A occurring, B and A bar. Or then it says A occurs and B at the same time. Well, we know that A and B occurring at the same time, A and B being mutually exclusive, is impossible. So this whole probability right here is 0. We can just ignore it, exclude it, it doesn't matter. Now we move on. Probability of B and A bar, or complement of A, is really same as probability of B. Why? Because remember that if B occurs and at the same time A does not occur, well, we know that because they're mutually exclusive. So we can just simplify this into saying, okay, it's the same event as if B just occurs, because A does not occur at the same time as a consequence of them being mutually exclusive. So this entire process takes us down to probability of B, which is given to be 3100th. Here is another example for us. Events A and B are mutually exclusive. Suppose event A has a probability of occurring of 600th, and event B occurs with probability of 4400th, and we of course know that they're mutually exclusive. Part A, compute the probability that A occurs but at the same time B does not occur. So A intersection B bar, or complement of B. Using the fact that A and B are mutually exclusive, we can simplify the statement to saying probability of A occurring and B not occurring at the same time means just probability of A occurring, which is given to be 600th. Our next part B, says to compute the probability that either A occurs without B occurring, or A and B both occur. Well, we know because A and B are mutually exclusive, this is going to be 0 and doesn't have to be counted. This statement, therefore, is what we need to find, probability of A and B not occurring. Just like before, we already computed that is same as 600th, and the problem is solved. Here is our last example. Events A and B are mutually exclusive. Suppose event A occurs with probability of 2600th and event B occurs with probability of 700th. So I'm recording everything I know so far, the probabilities of the given events and the fact that they're mutually exclusive. Part A is asking us to compute the probability that A does not occur or B does not occur, or both of these happen at the same time. Symbolically, we write probability of A bar, or A complement, or union B bar, B complement. Think about how we can rephrase this. A not occurring or B not occurring, because they're mutually exclusive, is same as A and B not occurring at the same time. But A and B itself, just this little portion right here, let me highlight it, just this little portion right here without the bar above it, probability of that is 0, or empty space, or empty set. Meaning, because they're mutually exclusive, A and B never can happen together, so probability is 0. So we're looking for a complement or inverse situation of getting 0. So not getting 0 or not getting empty set really means getting the entire sample space, or 1. So probability of this event of A not occurring or B not occurring is 1 or 100% chance. For part B, we compute the probability that either A occurs and B does not occur. That's what means A occurs without B occurring. Or B occurs without A occurring. We can look at each of these chunks individually. Because A and B are mutually exclusive, it is automatic that if A occurs, then at the same time B must not be occurring. So we can simplify this first statement into just A. And because B and A, again, are mutually exclusive, when B occurs, A automatically does not occur. I don't have to say it one more time, so I can simplify this into just B. In other words, I'm looking for the following probability. Probability of A or B. According to the general addition rule, probability of A or B means probability of A plus probability of B minus probability of intersection A and B. But because A and B are mutually exclusive, the intersection is 0. They cannot happen at the same time. So I just add the corresponding probabilities of A and B to get 33/100th.